Okay, so today we're talking about function applications. And, sometimes you can think of that as word problems. But hopefully they won't be scary word problems. All right, this is assignment number 6. And let's see. Okay, so first, write the formula for area of a circle. As a function of radius. Remember, when we talked about this before, we said this is our output, our dependent variable, and this is our input, our independent variable. Okay, so what will that look like? Write the formula for area of a circle as a function of its radius. Well, area of a circle is pi r squared. So if I write it with function notation, that's what it looks like. Area is a function of radius. The area depends on plugging in a radius, stuff happens to it, and out poops an area. That's all I have to do here. Write area as a function of radius. But what about write the area of a circle as a function of circumference? Well, that's a little harder, right? Because I don't know a formula called A of C, area as a function of circumference. I know A of R, area as a function of radius. I hopefully know that circumference is 2 pi r. So it turns out that this piece of prior knowledge is going to be my helping equation that lets me go from this area formula that I do know to the area formula that I want. So I want to solve for r. Solve that for r. So c over 2 pi equals r. Now in my area formula, where I see area is pi r squared, I can replace that r with some circumference stuff. So pi c over 2 pi squared. Now I have area in terms of circumference, not in terms of radius. I needed to bring this to the party and to solve that helping equation for r, so I could get rid of r and replace r with some c stuff. Not quite done here yet. C squared pi over 4 pi squared, right? We've got to square the c, the 2, and the pi. Now this pi can cancel one of those, and so we're going to end up with A of c equals c squared over 4 pi. That's area as a function of circumference. Nice. Well, let's take a look at this one. How about area of an equilateral triangle as a function of its side length. And let's call the side length x. Okay? What do you remember about equilateral triangle? Equilateral means all 3 sides are the same. So that's what we have, where each of them is an x. Okay? But I'm asked to write the area of that triangle as a function of x. Well, I know area of a triangle formula. Area equals 1/2 base times height. The problem is that this area isn't just a function of one variable, it's a function of both bases and heights. I need to get this to say a of x. Area is just a function of side length. Well, I notice here that the base of the triangle is x. So I could start, but what about the height? How do I find this height? Well, here's the thing. If this is an equilateral triangle, then it's also an equiangular triangle. And if all three angles are equal, what are we going to have? 180 over 3, 60 degrees. 60 here, 60 here, and this altitude bisects that 60 into 30 and 30. So now what I'm looking at is x. This side got cut in half, so that's a half of an x, and I'm looking for height. So we have two ways of finding that height. The first way of finding that height is the Pythagorean theorem. The second way for finding that height is to remember our shortcuts from geometry class about 30, 60, 90, and 45, 45, 90 special right triangles. Now, I've found recently that most students don't remember those from geometry, and they do remember Pythagorean theorem. So I'm going to show you the Pythagorean theorem way first. Remember, a squared plus b squared equals c squared. The hypotenuse always has to be alone on the other side of the equal sign. So I have x over 2 squared plus h squared equals x squared. Remember from algebra basics that we're going to apply that to both of these. And I'm trying to solve this equation for h, right? That's the thing that I still need. So I'm going to have to subtract this from both sides. So I'm going to have x squared minus 1/4 x squared equals h squared. Well, that's 4/4 x squared minus 1/4, so that's 3/4 x squared equals h squared. But we're not looking for h squared, we're looking for h. So we still need to take the square root of both sides. Well, what's that going to get me? Well, let's take a look. I've got the square root of 3 over the square root of 4, square root of x squared equals h. Now, I don't have to worry about the plus or minus here because my height can't be negative in this problem. But I can simplify, and I get that h equals root 3 over 2x. Okay, so I know that this is root 3 over 2x. And I know that this is root 3 over 2x. And so what's area as a function of side length for an equilateral triangle? A of x turns out to be root 3 over 4x squared. Ta-da! We wrote the area of a triangle not in terms of base and height, but in terms of side length. Okay? And whether we have to derive pieces, like we had to use the Pythagorean theorem to find h, or whether it's we happen to know a helping equation, like in that last problem, where circumference was equal to 2 pi r, and we could solve that for r and do a clever substitution, we'll be called upon to do some stuff like this in tonight's homework. Okay, what's next? Well, well, you know, I kind of wanted to go back to variation for a second. How about we'll call this bell work then, and say the area of a circle is proportional to the square of its radius such that A equals (36π) oh, sorry, this is the wrong problem. Oh, mercy. I meant to do, let's review variation with this problem. Y varies with x and inversely with the square of z, such that y equals 3 when z equals 6 and x equals 2. Find y when x equals 3 and z equals 5. Okay, there's a nice review bell work problem. Off you go, and come back when you're done. Okay, so did you build this variation model where you said y equals k x over z squared? So we vary with x, don't forget the constant of variation, and inversely with the square of z. So when I plug stuff in, 3 equals k 2 6 squared, it's going to be 3 equals 2k over 36. Guess that reduces to 18. And if I multiply both sides by 18, I get to 54 equals k. Am I done? No, it didn't ask for the constant of variation here, the constant of proportionality. It asked for what y would be equal when x is 3 and z is 5. So let's build our variation model. Y equals 54x over z squared. And now that we have this variation model, we can plug in x equals 3, and we can plug in z equals 5. So what will our problem look like now? Well, y equals 54 times 3 over 5 squared, or 162 over 25. That's what y equals. And I guess you could turn that into 6 and 12/25, but why would you want to? That's a fine answer for me. Okay, so let's then move on to these word problems that people get concerned about. Find the area of the largest rectangle that can be inscribed between the x-axis and y equals square root of 16 minus x squared, which is a semicircle with a radius of 4 centered on the origin. Okay, so I guess the first thing I want to do when I read a problem like this is not run away. And the second thing I want to do is I want to think about what's going on. 4, 4, 4. So I've got this semicircle, and what I'm trying to do in this space in here, inscribed between the x-axis and this curve, is I'm trying to imagine that there's inscribed here, drawn within, a rectangle. Now, there could be lots of different rectangles, right? There's that red one, We could have this green one. We could have this black one. All kinds of different rectangles here. But what we know is that even though there's an infinite number of possible rectangles I can draw, there's one rectangle whose area is bigger than all the others. All right, so that's the one we're trying to find, and we're trying to find the area of that triangle. I'm sorry, of that rectangle. So let's start with what we know. And I know you want to say, I don't know anything, Mr. Cooper, but I think we know some stuff. What's the formula for area of a rectangle? Okay, area of a rectangle equals length times width. All right, now here's what I know. If there's an ordered pair here on the curve, we call it x, y. X is the input, y is the output. So that means, since this is the origin here, it means that this distance is x. And because of symmetry, that's also x. So what can we say about the length of this rectangle? Well, I say it's 2x plus 2x. I'm sorry, it's x plus x for 2x. Now what about the width of this rectangle? Well, the width is this distance. And we know this distance is the y value of that ordered pair. This is the x value of the ordered pair. This is the y value of the ordered pair. So the width of our rectangle is y. Now I'm looking at area equals 2xy. And I have a problem. Area is a function of two different variables. I really want area to be a function of just one variable. So I need something. I need something that will say, let me get rid of this and replace it with some x stuff. Do you see anything here that we could use to help us get rid of y and replace y with some x stuff? Why, yes, keen observer. That is it. That's our helping equation. So, times square root 16 minus x squared. Now we have area all in terms of one variable. Okay? So, first question. I know that ultimately what I want to do is I want to find the area of the largest rectangle. But let's take it in steps. Step 1, write area as a function of x. And we can do that. We just did it. We said that area would be 2x square root 16 minus x squared. Okay? Now, as far as knowing the maximum, yeah, not very sure. This certainly isn't one of my reference graphs. I mean, I feel like I could sketch it, but I think I'd need to know some information. For example, is there a domain restriction on this problem? Well, I think there is. I think there's a domain restriction because I have a square root here. So let's ask the second question. What's the domain of a of x? Okay. Now I know I can plug any number I want into this linear thing. It's this square root that I'm concerned about. And what did we say about domain for square roots? We set the stuff under the radical, the radicand, greater than or equal to 0. And then when we talked about inequalities, I said, hey, you should turn that into equals for now and get 16 equals x squared, or x equals, now here is a case where when we're taking the square root of both sides, we want plus or minus 4. So I get these two critical numbers, -4, +4. And I recommend that we test some values on each of these intervals. If I plug a 0 in here, is 16 minus 0 greater than or equal to 0? Yes. How about if I plug a 5? 5 squared is 25. 16 minus 25, that's negative. That's not greater than or equal to 0. And if I plug in a negative 5 times negative 5 is still positive 25. 16 minus 25, no, that's not greater than or equal to 0. And if I plug in the point 4, 4 squared is 16. 16 minus 16 is equal to 0. So that's a yes, and that's a yes. So my domain, negative 4 to 4. So going back to the question, what's the maximum area? Well, I know the maximum area is going to occur somewhere between these x values. Somewhere between x equals negative 4 and x equals positive 4, I'm going to have a maximum area. All right, well, that can help. Last thing I want to think about is, where are the x-intercepts here? And remember, that's asking when a of x equals 0. So 2x could equal 0, or square root of 16 minus x squared could equal 0. If I square both sides, I get x squared equals 16, or x equals plus or minus 4. And over here, x equals 0. So when I think about graphing this, x-intercept, x-intercept, x-intercept. Now, anything that poops out of here is going to be a positive number, because it can't take the square root of a negative. So that's positive times, for x values bigger than 0, that's a positive. For x values less than 0, I'm going to have a negative times a positive, or a negative. So I know there's a maximum somewhere between 0 and 4 even. Well, I'm not going to be able to find it by hand, and not until I learn calculus. Once I've learned calculus, I can actually do that problem by hand. But for us, for right now, I'm going to go over to y equals, and I'm going to type in 2x square root 16 minus x squared. And my viewing window will go from negative 5 to positive 5, and my y values, well, they went down here, and if I plug a 2 in here, that's square root of 12. Square root of 12 is between 3 and 4, so let's say 4 times 4, 16. So I think I want to go plus and minus 20. Negative 20 to positive 20 in steps of 5. So what do I get? Oh, I still have my axes turned off. Hold on while I turn those back on. Oops. So format. Hello, format. Wow, you're doing something. What are you doing? You're doing. Second format, turn the axes on. Great. And I don't need this calculus graph. Okay, so I'm seeing this graph. And notice the limitations on your calculator. See how it looks like it stops here and it stops here? We already know where the x-intercepts are. There are x-intercepts here and here. The graph doesn't stop there. Your calculator is just having problems drawing something so vertical. Likewise, your graph doesn't stop there. We have an x-intercept here. Okay? So don't let your calculator's inability to show you properly make you say that something is happening that's not really happening. All right, so what do I notice? Well, I notice that I'm looking for that maximum area. So second, calculate maximum. Go to the right side of that maximum. I guess I want to be on the left side first. Take that back. Now go to the right side. And hit enter. And do I want to guess? No. So I hit enter a third time. And I end up with 2.828. So that's our x value. And what is the area there? The area at this point is 36. So that's the area of the largest rectangle that can be inscribed inside this semicircle. And so it went from 2.828, negative 2.828, and this y value, remember we said that y was equal to the square root of 16 minus x squared. So I could take this and plug it in there to get a y value. Or I could take that area that we found the maximum area here was equal to 36. And we could do 36 divided by 2 times 2.828. And if we did that, that would find y for us. So if the question had been what are the dimensions of this rectangle, I would say 36 divided by 2 times 2.828. And I should have done that on the main screen. So 36 divided by parenthesis 2 times 2.828. Close parentheses. 6.365. 6.365. So the dimensions are this 6.365 by 2 times that number, 2 times 2.828. And I get this length is 5.656. So the largest rectangle occurs when y equals this number and x equals this number, and it occurs that way because we're bounded by this upper curve. All right. I really appreciate that the area turned out to be a whole number, while the x and y values turned out to be radicals. I think that's very interesting. Okay, so there's our first problem. There was a bunch of stuff to do in it, but finding the maximum we didn't have to do by hand. We did that on the graphing calculator. Second, calculate maximum. And that should be something that you're comfortable with. If not, you might want to go back to assignment 7 in the graphing basics unit. That was when we had our calculator use lab. And there's a video for that. You could go and watch it. Okay, let's take a look at our next function word problem. You throw a bag of chips to your socially distanced friend. Socially distanced 5-foot tall friend. The model h of x equals negative 1/10 x squared plus 3x plus 6 gives height h as a function of x horizontal distance away from you in feet. Okay, so here's our question. Actually, I have a couple of questions here. Um, here's our question. If your friend is 30 feet away, will he catch your chips? Okay, so how can I do that? Well, I think on one hand, I can try and figure out when my friend is 30 feet away, what will the height be? What will the height be? You know, if this is height as a function of how far away he is, and 30 feet away, I think I'm supposed to find, in this problem, h of 30. Now, you can certainly plug 30 in and 30, and I instead, though, am going to go to y equals. I'm going to type in our function negative 0.1 x squared plus 3x plus 6. And then go over to the table. I've gone over to the table, and I'm typing in 30. Oops. I'm typing in 30 into the table. There we go, and hitting enter. So when I plug in 30, I get y equals 6. Y equals 6. So we know the height of the bag is 6 feet at 30 feet away. Well, your friend is 5 foot tall. Will they be able to reach up for that 6-foot bag? Can you reach a foot over your head? I think you can. So I think your friend has a good chance of catching this bag of chips. Okay. We could certainly pose the question this way. This would also be a way to ask a question. What is h of 30 in the context of this problem? Okay, so I would say h of 30 equals 6, or the height of the chips is 6 feet when the bag is 30 feet away. And by away, I mean away horizontally. Okay? Great. I think that that's in the doable place, if you ask me. This is a hard problem for people, not because the math was hard, but because they don't think about what the words are meaning. Like they see height, and they see as a function of horizontal distance, and they say, yes, so. But then when we're told that your friend is 30 feet away, or even just given h of 30, the students tend not to make a connection between that notation and this function. This is say I'm plugging in a 30 for these x's. We know x's is the horizontal distance away. So I'm trying to say, hey, what's the height when the horizontal distance is 30? Okay. Third problem. Third problem is a classic. You've got a square piece of paper, and you cut out little squares from each corner. Cut them out. Ding, 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 ding. And then you fold along these dotted lines. And that's going to create an open-topped box. Okay. And our question is going to be, if you started off with a 10 by 10 inch piece of paper, and you're trying to figure out how big these squares should be that you're going to cut out so as to make the volume of the box be a maximum volume. You want the box that holds the most stuff. How big should X be? How big should X be in order to maximize area volume? Volume is what we're trying to maximize of the box. Okay? So, alright, this is going to take some thinking. And, you know, I want to say something about this problem. You're going to see this problem now in our functions unit, but you're also going to see this problem again, just like the last two problems. You're going to see this one again in our polynomials unit. Not going away. Gonna see it again. Gonna see this a bunch of times. Okay? So please make sure you know how to do this problem. Okay? Alright. So here's what I know. I know that the volume of the box is length times width times height. But what I'm wanting is volume in terms of x. So I have to write this in terms of x, and this in terms of x, and this in terms of x. All right, well, let's see. This length here corresponds to this length here. So how long is that green segment? Well, we know that this length is 10, and that this much is x, and this much is x. So if I take that 10, and I take away an x, and I take away an x, I'll have that segment. So this is 10 minus 2x. Okay? Now, what about the width? So there's the width, and that corresponds to this. So how long is that? Well, this is 10, and we're taking away an x and an x to get this. So that's 10 minus 2x. And what about the height? Well, the height is here, and that's this. And those are x's. So I can write volume as a function of x, 10 minus 2x, 10 minus 2x, times x. Length times width times height. If you like, you could write it like this. Why might you like to do that? Well, I'll tell you. Because for graphing purposes, you know that there's a bounce at x equals 5. And you know we pass through at 0. If I were to FOIL this out, negative 2x times negative 2x is positive 4x squared times x is positive 4x to the third. So we know our graph is going to go up that way and down that way. We're going to pass through at 0 and bounce at 5. So there's my graph of volume. Okay? How big should x be in order to maximize volume? Well, I could have a maximum here. Maybe there's a maximum over here. So I'm not quite sure yet. So let's break this up into steps. First step, write v of x. Okay? So we wrote v of x. We used the picture, we labeled the box, we thought about length, width, and height, and we replaced. Okay, that was v of x. Now, what about this? What about to the domain of v of x? Okay, because, you know, when I think about a third-degree polynomial with a positive leading coefficient, I think about, I can plug any number I want into that. Well, yeah, except this is a word problem, and because this is a word problem, these letters have a real-world meaning. So that's the length of the side that I'm cutting out of the box, and this is the volume that gets made when I cut that length of side out. So here, That's a negative x. And it produces a negative volume. Can I have a negative volume to my box? No. No one wants a box with a negative volume. That's a sad box. You can't get any presents in there. They're all on the outside of the box. Okay, so no negative volumes. No, I can't cut negative 5 inches off each side. Is that adding 5 inches? So I can't have any of these. Okay, well, I still have all of these. What about over here? What if I plug in a 6? What's the problem with that? I mean, this model says the bigger and bigger x value I plug in, the bigger and bigger the volume will be. Whee! As I go this way, the function heads to infinity. Yeah, except you've got a boundary over here. So we know the boundary is that this whole side is 10. Can I cut 20 off of this end and 20 off of this end if the whole piece of paper is only 10 inches wide? No. No, I can't. So what is the most I can cut? Can I cut 10 off of each side? 10 from here and 10 from here? No. That would be 10 and 10 or 20, and the whole thing is only 10. What if I cut 5 out from each? So if I cut 5 from here, 5 from here, that uses up the whole 10 evenly, but doesn't leave me any extra left over for the side. So I think that 5 is the largest I can do. And it's only with numbers between x between 0 and 5 will I actually get a volume. So I'm looking for this maximum volume, and I know to set my x window to go from 0 to 5. Okay, so let's think about this. We're going to type in our function into y equals, and our function is x times 10 minus 2x quantity squared. And I'm setting my viewing window to go from 0 to 5. Now, what about the y values? Well, I don't know. How about negative 10 to, oh no, I hit clear. Negative 10 to positive 10. Graph. I don't see much of it, Mr. Kukla. I see a little bit over here, and I see an almost vertical thing over here. Where's the rest of the graph? Well, remember, we're looking at this part of the graph, and I see this in the window, and I see that in the window. So I know that my maximum is way higher above. I also know that this is a cubing function. And if I put something like 3 in and cube it, I get 27. And if I get 4 in and cube it, I have 64. So I think I should try a bigger y value. I also realized that volume can't be negative, so my y value can go from 0, let's say 100 in steps of 5. Well, look at that. That's fabulous. And so now I see the graph. I think you can see it too. There's the graph. It's got its maximum. And we'll just do second, calculate maximum. Bring our cursor to the left of the maximum. Hit enter to the right of the maximum. Hit enter. No, I don't want to guess. And so I get that the maximum volume occurs when x equals 1.666, which is 5/3 inches, and the maximum volume is the other number. Remember, this was a graph of volume, not x's and y's. The maximum volume was 74.074 inches cubed. Okay, and if they wanted the dimensions of the box, well, I know that this length is 10 minus 2x. So 10 minus 2 times 5 thirds. So 30 thirds minus 10 thirds is 20 thirds. So this is 20 thirds. This is the same. It would also be 20 thirds. And this is just x, which is 5 thirds. So we could say that the dimensions would be 20 thirds by 20 thirds by 5 thirds. Length times width times height to make this volume. Okay, so we wrote v of x. We considered the domain of v of x. And then we used our calculator to find out what x we should cut to produce a maximum volume. We were even able to find the dimensions of that box that would contain the maximum volume. Okay? All right, so now what I want to do is I want you to answer the same question, except that this time you don't have a square piece of paper. This time, this distance is 14 inches. This is still 10 here and here, but this distance is now 14. And so I want 1, volume of the box as a function of x. 2, I'd like to know the domain of v of x. And 3, what are the dimensions of the box with the largest volume. Okay, so please pause the video, find v of x, find the domain of v of x, and figure out what the dimensions of the box with the largest volume would be. Okay, I'll see you in a few minutes. Hey, so welcome back. So we're still going to make this open-topped box. This, however, is now 14, and so this, which is this, is going to be 14 minus an x minus an x. So 14 minus 2x. This over here still produces this side length of 10 minus 2x. And the height, when I lift this flap to this flap, is still x. So v of x is x, 14 minus 2x, 10 minus 2x. Okay? Now, what about the domain of v of x? Well, let's take a look at this graph. We've got x times minus 2x times minus pi 2x, that's positive x to the third. And then I also know that I have zeros at 0, 7, and 5. 0, 5, and 7. I don't see any multiplicities on any of these factors, so I know I'm going to be passing through on all of them. And it's a positive x to the third, so I'm going up and down. So that's what my graph looks like. Here's x, here's volume. Now, let's think about restricting the domain. Can I have a negative volume? No, I cannot have a box with a negative volume. So that gets rid of those, and that gets rid of those. What about over here past 7, like 10? Can I cut 10 inches from this side and 10 inches from this side if the whole thing is 10 inches? Well, no. The most I could cut out from each side is 5 inches because the whole thing is 10. So this is not possible. I can't cut out more than 5 inches from each side. So here's my domain. The domain is from 0 to 5. Now, why did I use parentheses there instead of brackets? Well, if I include 0 and I include 5, when I put those numbers into this volume equation, I get 0. And it's kind of a stupid box that has a volume of 0, isn't it? So I'm not including the things that make the volume equal to 0. Okay, so we've got 2 parts done. The last part is to find the maximum volume, or the dimensions that make that maximum volume. Now, how do I find that point? Well, that's what my calculator is for. I'm going to go to y equals, and I believe I still have my first box in here. So let me just modify that. Parentheses 14 minus 2x. Okay, and my viewing window goes from 0 to 5. I know I need to go past that. So I'm going to go 0 to 10 now. And I'm not sure if 100 will be sufficient, but we'll see. Okay, well, 100 was not quite sufficient. So let's go a little higher. Window. Okay, so I want to go to 200 in steps of 20. And it was a little weird seeing this cut off, so I'm going to go negative 10 to 10. I thought I did negative 10 to 10. Clearly, I did not. Hello. It's graphing something though. I think I need to turn that off. Yeah, negative 10. Oh, x values. No, I don't need x values going to negative 10. I need y values going to negative 10. Okay. Nice. Nice. Okay. So, I'm looking for that. See? Look at it go. What is it trying to do? Part of a piecewise function. Yes, it's the derivative of a piecewise function. Alright. That's gone. We won't have to worry about that again. Bum, 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 bum. And I'm doing second. Calculate maximum. Move to the left side of the cursor. To the left side of the maximum. That's going to be over here. Enter. Go to the right side. Hit enter. Guess. No. So I get the ordered pair 1.918, comma 120.164. Now remember, this is not x and y. This is x and volume. We're looking for the dimensions of the box that makes the biggest area, the biggest volume. We know that biggest volume, inches cubed, is that number. But what about the dimensions of the box? Well, we want length times width times height. We know the height is 1.918. But what about the width and the length? Well, I'm going to have to take that x value and plug it in here. I have to take that x value and plug it in here. So, if I take 14 minus 2 times, oops, wrong screen, 14 minus 2 times 1.918, I get 10.164. And if I do 10 minus 2 times 1.918, I end up with 6.164. So, the dimensions of my box that make the biggest volume. The dimensions of the box with the biggest volume, 120.164, would be 10.164 inches by 6.164 inches by 1.918 inches. Ta-da! All done. Okay, let's take a look at our last problem. Our last problem is a shipping question. And if you go to the post office, especially if you talk to an older teller, they'll have a piece of string or a chain. Maybe if they're younger, they'll have a tape measure. But the post office says that there is a maximum girth plus length to any box you can send with them. So girth is this plus this plus this plus this. So if these are all x's, we're saying the girth is 4x. And the length, well, let's call that y. So what do we know about girth plus length? Well, I believe with the post office that they say maximum of 108 inches. Okay, so then we ask the question, what is the maximum volume for this box? Well, I remember from middle school that volume of a box is length times width times height. So volume is x squared y. So is volume in terms of one variable right now? Is volume a function of just one variable, or is it a function of two? Yeah, it's a function of two, so I really want to get v of x. I want to get volume in terms of one variable. If only I had a helping equation that could help me get rid of y and replace y with some x stuff, that'd be fabulous. Look, this green thing. This has a y in it and an x in it. I bet I could use this as a helping equation if I subtracted 4x from both sides. And so now I can take this and plug it in there. So I get x squared times 108 minus 4x. Fabulous. So let's take a look at the graph. This time when I distribute, I get negative 4x to the third. So I know it's up over here and down over here. I also see a multiplicity of 2 at x equals 0, so I know I'm bouncing at 0. Over here, how do I find that y-intercept, or in this case a v-intercept? Sure, I set that equal to 0. X squared equals 0, and 108 minus 4x equals 0. So 4x equals 108, and x equals 27. So this is 27. So I see that there's going to be a maximum volume somewhere between 0 and 27. And the cool thing is it's probably not going to occur exactly halfway between. It's very, very rare when that happens with polynomials above second degree. So, volume. This is our volume equation. There's v in terms of x. But what about the domain? Well, can I have any negative side lengths? No. So all this gets thrown away. Can I have any negative volumes? No. So all this gets thrown away. Because anything out here is going to produce a negative volume. And anything over here with a positive volume produces a negative x. And neither of those things is okay. So I'm going to say that the domain goes from 0 to 27. Okay. And then finally, how do we find the volume of this box? So I'm going to type that equation into y1. I've got x squared times 108 minus 4x. Delete the rest of this stuff. And I know my viewing window should go from 0 to 27. So I'm going to change that to 30. And, this is still a cubing function. If I plug in 30, and I square it. That's 900. So I think I want to change my y max to 1,000 and see if I see what I need to see there. Graph. Okay, so I don't know if you can see, but we're a long way away from the top. Huh. So, I did 1,000, didn't I? But look, 30 cubed is 30 times 30 times 30. It's 27,000. So let's plug in 27,000 and go in steps of 1,000. Graph. Now I see my maximum. Second, calculate maximum. And on the left side, hit enter. Go to the right side. Oops, I got off it. Start again. Second, calculate max. Enter. I did it again. Second, calculate max. Enter. Scooch over and hit enter. Guess, no thank you. And I end up with x equals 18. So this is x equals 18. Is that halfway between 0 and 27? No. And the maximum volume is 11,664 inches cubed. All right. So when x is 18 inches, what would y have to be? Well, remember we had that helping equation, y equals 108 minus 4x. So 4 times that is 72. 108 minus 72 is 36. So the dimensions of our box will be 18 by 18 by 32 inches. 32 long, 18 by 18 over here. This produces a max volume of 11,664 inches cubed. All right. Oh, did I say 120? I'm sorry. I said 108. I meant 120. So AP has started using this phrase. I love it. It is known. By whom? It is known that shipping with United States Postal Service, the maximum girth plus length can be is 120 inches. Please find the maximum volume and dimensions of the largest, that means most volume, box we can send. Okay, so, and if it helps, get a picture of the box. And yes, these are squares on the ends, and we're putting y here. All right, so give this one a try and come back when you're done. I'm looking for the dimensions of the largest box as well as the maximum volume. Hi, welcome back. So volume is 2xy, but I want to get rid of that y and replace it with some x stuff. So I look up over here and I say, okay, girth plus length for x plus y equals 120. That's my helping equation, and I call it a helping equation because it's going to help me rewrite volume so that I don't have any y's. I know from my helping equation that y equals 120 minus 4x. So I can replace this y with 120 minus 4x. Okay, so now I have volume all in terms of one variable. Great. We have x equals 2x 120 minus 4x. You're welcome to distribute if you want. But the nice thing I find about factored form, sorry, I dropped, that's x times x. So that's x squared, not 2x. Okay, so that I see my intercepts for this volume function. So my graph has a negative leading coefficient. So this end is up and this end is down. I see a bounce at 0. And this intercept is 120 divided by 4, or 30. Okay, so I know my viewing window should go from 0 to 30. And I'm looking for this maximum. Well, great. Let's see what we can get out of our calculator. If I go to y equals, I want to change that function to be 120 minus 4x. And then I'll hit graph. My volume is definitely larger. Second, calculate x. That's the left side. Let's go over to the right side. Okay, and hit enter and enter again. So I get when x equals 20, volume equals 16,000 inches cubed. Okay, it's a lot of inches. Is it really 16,000? Yeah, it is. Okay, so what are the dimensions of this box? Well, we remember that the box was x by x by y. And we know that x is 20. So 20 inches by 20 inches by... Now, is this our y? No, remember this is a graph of volume as a function of x. This is the maximum volume. Max volume is 16,000 inches cubed. So how do I find this y value here? Because I remember that the volume of the box is x times y. Well, remember we had that helping equation, 120 minus 4x. And if x is equal to 20, 4 times 20 is 80. 120 minus 80 is 40. So these are the dimensions of the largest box, and that's the area of that box. If I multiply this times this, I get that. All right, well, those are your word problems, and you're going to see them in the homework. So, you know, if you need to watch the video again so you're not as scared, watch the video again. But definitely do the homework, because if you don't own this stuff, it's not going to be in your brain when you go to take a quiz or test on it. All right, have a great day.